When we left off yesterday, we had defined our area under a curve as the limit as n approaches infinity, so we could have an infinite number of subintervals, an infinite number of rectangles, and we said that we could choose left endpoints, right endpoints, or midpoints, or any other value in that interval. And so that's what we were using this little star for. When we said f of x sub 1 with the asterisk up here, that meant choose any value in that first subinterval that you want, left, right, mid, or something else. And then we were multiplying it by the change in x because that was base times height, so that was the area of the first rectangle, plus the area of the second rectangle, all the way down until we got to the area of the last rectangle. And we said another way to sum that up would be to keep that limit notation out in front, but we could write this as a summation. And the way that we would do that is we would use sigma notation to say the summation from 1 to n of f of x sub I. So that means start by putting 1 in here and stop when you get to n. So that would be f of x sub 1 plus f of x sub 2, f of x sub 3, all the way down until we got to our last one, and of course being multiplied times the change in x. So today they say, let's take that same notation that we finished off with yesterday that was going to be our definition of area under a curve, and let's define that as a definite integral. So on page 324, it says the definition of a definite integral is if f is a continuous function. That's like the beginning of everything we see now, right? It has to be a continuous function. If it's not, then everything else after that is irrelevant. If f is a continuous function defined between a and b, we divide that interval ab into n subintervals of equal width so that the change in x is equal to b minus a over n. We let x sub 0 be the a value and x sub n equal the b value. Those are the endpoints of the subintervals. And we choose sample points, x sub 1 star, x sub 2 star, x sub 3 star, to be any value in those subintervals that we want. Then the definite integral of f from a to b is defined by exactly what we see here. The definition that we finished with yesterday is going to be rewritten with this notation, and that will be our notation for a definite integral. All right, let's look at each piece of it. This first piece that we have is our integral sign. So it's the it looks like an elongated S to remind me that an integration is literally just a summation. A and B are going to be my lower limits of integration and my upper limits of integration. They tell me where to stop and start. F of x is my integrand, so my function is my integrand. And then dx always goes along with an integral sign. You won't see an integral sign without a dx along with it. So that's kind of the equivalence of what we had over here. This told me where to start and stop and to do a sum. So that's the same thing as my integral sign. This gave me the function that I was using, so that's the same as my integrand. And then we had our change in x on the end here, which is going to be very similar to a differential dx later on. But in essence, this dx goes along with our integral sign. This is also called a Riemann sum, named after Bernard Riemann, a mathematician and scientist. But anytime they ask me to do a left endpoint, a right endpoint, midpoint, or they say find a Riemann sum, it's the same thing. Alright, so not really a whole lot that we can do with these, but in example number 1 it says we want to express the limit as n approaches infinity from 1 to n of this function with a definite integral, and we want to use the interval from 0 to pi. So to begin with, I'm going to know that I start at 0 and I stop with pi as my upper and lower limits of integration. Then I need to find my integrand. And my integrand is just going to be my function. And if you'll notice, if I take off the subscript of I, that basically gives me the function for my integrand. So if I take off these little i's down here, I'm going to have x cubed plus x sine x, and that is my integrand. And then remember, we're always going to put that dx on the end because the dx always goes along with the integral sign. So that's how we could convert the notation from yesterday to the definite integral notation for today. All right, the last thing that we want to look at today are some formulas that we're going to need. On page 327 in your textbook, they give you some formulas for evaluating integrals. The first three are formulas that we've seen before. The first one is our sum of integers formulas. So let's say that you wanted to find the sum of the first 100 numbers. Instead of doing 1 plus 2 plus 3 plus 4 plus 5 plus say all the way up to 100, all I would have to do is say, look, I'm trying to find the sum from 1 to 100, so I'll put 100 in the place of n. So that would be 100 times 100 plus 1 over 2. 100 times 101 divided by 2. If I were trying to find the sum of squares, that would be like the sum of the first 15 squares, like 1 squared plus 2 squared plus 3 squared plus 4 squared. Then I could say, okay, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4, all the way up to 15 squared is 225. Instead of having to do that, since 15 is in the place of n, then I can just come over here and say that's going to be 15 times 15 plus 1, 16. Times 2 times 15 plus 1, 31. So I'll have 15 times 16 times 31 divided by 6, and that would give me the sum of those squares. Sum of cubes formula, same idea. If I wanted to find the sum of the first 10 cubes, that'd be like 1 cubed plus 2 cubed plus 3 cubed all the way up to 10 cubed. I can just put 10 in the place of n. And so that's going to be 10 times 10 plus 1 over 2 whole thing squared. So 10 times 11 over 2, that whole thing squared would give me that sum. The last couple of properties that we have down here will make finding summations a little faster and easier. The first one says if you have the summation from 1 to n of a constant, then it's going to be n times that constant. For instance, if I had the summation from I is equal to 1 to 5 of the constant 7, it's the same idea as, let's say that you are graphing y is equal to 7, and you make an xy chart. It doesn't matter what you put in for x, you're going to get a y value of 7. So you can put in some crazy random thing and you still get a y value of 7. The reasoning behind that is there is no x in this equation to put a value in for, so it does not alter that 7. The same concept is going on when I have a summation of a constant. This says put 1 in for I. I don't have an I, so it's completely unaltered. I just get the value of 7. So when I plug in 1, I get 7. When I plug in 2, I get 7. When I plug in 3, I get 7. Plug in 4, plug in 5. So instead of sitting here and writing this number over and over again, however many times I have for n, it's a whole lot faster to just say, take n, the number of times you're going to write this number, and multiply it by your constant. So you can see if I would have just done 5 times 7, I would have gotten that 35. So this summation of a constant will make things a lot faster. The next one they give me is if you have the summation of a constant and times a value, you can move that constant out in front and then do your summation. And when you're finished with the summation, multiply by the constant at the end. The next one they give me is, actually they write it as two separate formulas in the book, and I've combined it into one, and that is the summation of two things being added or the summation of two things being subtracted. So let's start with adding. If I have the summation of two quantities are being added together, I can break that into two separate summations and find the first one and then add the second one. If instead of this plus sign I had a minus sign, if this was the summation of one quantity minus another, I can make that the first summation minus the second summation so that I break it apart.